Hey guys, welcome to video 96. Today we're going to wrap up our discussion of thyristors by taking a look at color organ circuits, and I'm also going to introduce the basic theory behind Electret microphones because I'm going to use those in a couple of circuit examples. But first, let's do a real quick review of the previous material we covered on thyristors. Starting over here on the left-hand side, the first thyristor we looked at was the 4-layer diode, and a typical application for 4-layer diodes is in the design of relaxation oscillators like I have shown here. The output voltage waveform from anode to cathode is shown below, and the frequency of this waveform is given by this equation, which was derived back in video 94 if you want to see where that comes from. The next thyristor we talked about was the silicon controlled rectifier, or SCR, and here we have an SCR used in a typical light dimmer circuit. Now this approach is called phase control because we're using the voltage drop across this capacitor to trigger the SCR, and the voltage across the cap is going to be lagging in phase relative to the line voltage applied to the circuit. Using an RC circuit over here gives us wider control of the conduction angle of the SCR compared to what we could get with just a purely resistive voltage divider over here. Now, typically we're going to have a 4-layer diode in series with the gate of the SCR, and this gives us a more well-defined trigger point and also prevents the SCR from loading down the RC control network over here because the 4-layer diode acts as an open circuit until it breaks down. Now, the device I have shown here, the DB3, is not actually a 4-layer diode. It's a TRIAC, which is like a bidirectional 4-layer diode. And in order to make it behave like a true 4-layer diode, I stuck a regular silicon rectifier in series with it. And that's the only reason D3 is in this circuit. Now, one of the disadvantages of using SCRs as load controllers is that they're half-wave devices. That is, we can only get conduction during the positive half cycle of the AC line, and we can see the load current waveform down here shows that we don't get any load current during negative going half cycles for the AC line. And we can fix that problem by creating what's effectively a bidirectional SCR, and that's shown over here. It's called a TRIAC. And what I've done is simply replaced the SCR with a TRIAC. I left the DB3 in the circuit, but I used the correct schematic symbol over here since it is a TRIAC, and I took the diode out of the circuit. I don't need that. I left the RC trigger circuit almost the same, but I had to increase the value of the pot to 100 k ohms to get full control of the conduction angle because the TRIAC has a more sensitive gate than this particular SCR that I used. So using the TRIAC, we are able to get wider control of the conduction angle, and as you can see here with the total resistance set to about 10 k ohms, the TRIAC has a conduction angle of 250 degrees versus the SCR, which gives us a conduction angle of 125 degrees. Okay, so that's enough review. If you want to see more, go back to video 94, but now let's move on to our main topic of interest, and that is color organ circuits. But first I want to note that these circuits are for educational purposes only. I built them so you don't have to, and you know, since you're working with the AC line and we're connecting things sometimes to a stereo or another amplifier, you know, it can be a little bit tricky. So I recommend that you don't mess around with these unless you really know what you're doing and you're extremely careful. But with that out of the way, let's go on over and take a look at the first circuit, and that is the classic old school color organ. These are the kind of circuits that I worked with back in the day when I was in high school, and typically what we would do is connect it directly across the speaker leads of the stereo or the radio or whatever audio source we had over here on the left. We used a transformer to isolate the amplifier from the line voltage stuff over here, and usually we'd use a step-up transformer with a ratio somewhere around 5 to 1, and that allowed us to trigger the SCR with a relatively low amplitude source over here, or a low power amplifier. So the transformer provides isolation between the line and our load here, and it also is typically used to step up the voltage so that we get enough to trigger the SCR, and this voltage divider formed with pot R1 just controls the sensitivity of the circuit. So basically what we're doing is triggering on the SCR at random times during the AC line cycle over here, and we generally get lamp brightness that's proportional to the loudness of the audio source. Now, the operation of this circuit is really pretty decent for as simple and primitive as it is, but one of the things we usually did was split the audio signal into low, mid, and high ranges to get a little nicer effect, and that's shown over here in this next version. Now, there are a couple different ways we can approach this. You could use one transformer over here and drive all three SCRs through different RC combinations here to split up the frequency bands. I used some transformers that I got off of Amazon that were really cheap. Here's a picture of them. They're EE14s, and they have a impedance ratio of 8 ohms to 1.3 k ohms. I measured them myself, and the turns ratio is actually 1 to 5. The DC resistance on the primary is 5 ohms, the secondary is 90 ohms. But in any case, they are stepping up the audio signal, and I found that rather than connecting them in parallel, this circuit works better if I connect all of the primaries in series. We get a little better frequency selectivity out of the circuit, and I'm not actually showing component values here because the SCR version doesn't work nearly as well as the TRIAC version, and that's what I'm going to show you next. But just a couple of other things to notice. These are pretty small transformers, but they're very inexpensive. I think 10 of them cost around $6, so you can't go wrong there. And the lights I used were just Christmas light bulbs. You'll see them in a minute. Here are the pinouts for the SCRs, and when you're building this, if you're going to be taking measurements, you have to pay close attention to the polarization of your plug over here, because if you're going to be using the scope to probe around in here, you don't want to connect the ground lead of the scope to the hot side of the circuit. So just be aware of that. I recommend that you don't build this. Like I said, I built it so you don't have to. But anyway, let's go on over and look at a little better version of this using TRIACs. Now, what I've done here is simply replace the SCRs with TRIACs. I used BT134-600s. These are sensitive gate TRIACs with a breakdown voltage of 600 volts. A quick look at their data sheets. We can see that these are good for an RMS on current state of 4 amps, and they can handle peak currents of 25 amps. So they're more than sufficient for your typical color organ application where you may have 4 or 5 Christmas lights in parallel on each channel. Now, you guys know that whenever possible, I like to build these circuits to demonstrate them for you, and this is no exception. But in order to avoid getting copyright strikes and things like that, I didn't want to use regular audio, this playing over the radio or something, or an album, whatever. So I'm just going to be playing some snippets of songs on the acoustic guitar. And in this case, I'm going to be playing into an amplifier, and I have this circuit connected to it, and you can see how it works. Baby, I Love Your Way by Peter Frampton. So there you go. The circuit actually works pretty well, but the one thing I don't like about it is connecting this high voltage stuff through these little transformers to an expensive stereo or some other amplifier. So what I'm going to do next is look at a way to integrate an amplifier into the circuit so we can have this all self-contained in a box where it's much safer. And in order to do that, I'm going to have to cover the theory of Electret microphones. So let's take a look at that next. Okay, if we want to make the color organ self-contained, we're going to need a built-in amplifier and a microphone to pick up the sound. And usually what we're going to use in this kind of application is an Electret microphone. Here's a picture of one. They're usually pretty small, and underneath it here is the internal construction. We've got an aluminum capsule, and inside it are two plates. The red one shown here on the left is called the Electret, and it's a permanently charged dielectric material. It's analogous to a permanent magnet, except it has an electrostatic charge. And to the right here is a conductive plate, and when sound enters through the port here on the left, it causes the Electret to move closer or further from this plate, and that induces a small signal on this lead. Typically, this signal has an amplitude of about 5 millivolts peak to peak, which is pretty small, and because the basic structure of the microphone itself is similar to a capacitor, we've got a very high impedance source with a low amplitude output signal. And in order to make this more compatible with typical loads, an internal JFET is included to mainly provide impedance transformation to step down the impedance, and it also can provide a little bit of voltage gain as well. The equivalent internal circuitry is shown over here, and you can see that we need to add an external drain resistor to the JFET and capacitively couple the output to whatever we're going to be driving. The characteristics for the typical JFET found in these applications are a pinch-off voltage of about 1 volt. IDSS maximum is around 0.5 milliamps. Usually it's a bit less than that. And the transconductance is about 1 millimho. And down below are the drain curves for this typical device. Now, the data sheets for Electret mics are usually pretty sparse. Here's an example of one. And you can see it gives us some basic parameters here. Maximum operating voltage 10 volts, usually operates around 2 volts. Output impedance 2.2 k ohms. That's the drain resistor that we would add, and some other information, but really not too informative. But I did a little experimenting with them, and with a VCC of about 3 volts and a 2.2 k ohm drain resistor, the gain was close to 1, and we get an output voltage of roughly 5 millivolts peak to peak. For higher VCC values, we'd use a larger drain resistor, and we can get higher gain out of the amplifier here as well, reaching a maximum of around 40 millivolts peak to peak with a 10 volt power supply, and that's the maximum that they recommend for these kind of microphones. And remember, these are just ballpark figures. They're going to vary a little bit from one microphone type to another, but they'll get you close enough. Alright, so that's enough about Electret microphones. Let's go see how these things are applied in the design of a self-contained color organ. Alright, here's the first version of the circuit we're going to be working with, and we're going to look at several different variations of this, but they're all going to be built around the LM324 quad op amp. This is just a general purpose op amp that's very good for low precision applications like this. And since we're operating off of a single 15 volt power supply, we're going to have to establish a reference voltage at 1/2 of VCC, 7.5 volts, and that's what this voltage divider over here with R1 and R2 does. It gives us a reference voltage of 1/2 VCC, and we're going to apply that to the non-inverting inputs of each of the op amps to bias them up. Now, because I haven't covered the theory of op-amps yet in this video series, I'm not going to go deep into the analysis of these circuits. Trust me, we're going to get into that, and not only will you be able to design circuits like this, you'll also be able to design the stuff that goes inside these op-amps before we're done. But for right now, I'm just going to kind of lightly gloss over what's going on here. So if we come over to our Electret microphone, this 10K resistor R3, that's the drain resistor, and we're connecting it to our 7.5 volt reference voltage here. So we've got a supply voltage for our Electret of 7.5 volts with a 10K resistor. That's going to give us an output signal into C2 of probably around 25-30 millivolts peak to peak typically. That signal is applied to the input of U1A, which is configured as an inverting amplifier, and we can adjust the gain with R4 anywhere from a maximum of 50 to a minimum of around 8 or so. The output of this first inverting amplifier is applied to these three op amps, which are also configured as inverting amps, and they've all got the same gain. It's -47 for each of them. The outputs are then applied to each of our TRIACs, and our filtering for the different frequency bands is taken care of here by these coupling capacitors. So our low frequency band has a coupling cap of 1 microfarad, and 0.22 microfarads for the mid-range, 0.1 for the high frequency band. And the individual channel sensitivity is adjusted with these 1K ohm potentiometers. And just like before, I want to give you guys a demonstration of how the circuit works, and to avoid copyright strikes, I'm going to have to subject you to a little bit more of me playing the guitar. Hopefully it's not too bad. And also, when I show the circuit, the transformers are still mounted on the proto boards, but they're not in use. That's from a previous example. So just disregard the transformers, and here we go. Here's some Plush by Stone Temple Pilots. Okay, so we see that this circuit works pretty well in spite of my playing, but I'd like to make a few modifications here. I want to move these adjustment potentiometers for each channel away from the high voltage section, and I'm also going to move the frequency selective filter networks over here to the inputs of the op amps. So let's take a look at that modification next. In this version of the circuit, we've got the same coupling network for the gates of all the TRIACs, 1 microfarad and 1K ohm, and we've got an adjustable resistor in the feedback loop of each of the inverting amplifiers to vary its gain. Since we have a 10K ohm input resistor on each stage, the maximum gain is 50, or actually -50, and we can decrease the gain to 0 for each stage as well. And while I'm at it here, the gain equation for all of these inverting amplifiers is AV equals -RF over R1, where RF in the case of these ones is a maximum of 500 k ohms. Over here it's 100 k, and R1 is just the input resistor, 10 k for these three, and 12 k or whatever on the input of this one. So coming over here to the input of the op amps, you can see we're using different coupling capacitor values to set our frequency ranges, low frequency on top, mid here, and high frequencies here. And these are all high-pass filters, and the corner frequencies are FC equals 1 over 2 pi RC. For this top filter here, the corner frequency is 72 hertz. For the middle one, it works out to be 480 hertz. And for this lower one, we've got a corner frequency of about 1.6 kHz. And you can mess around with different capacitor values to, set it however you like. But that's what I'm using here. And now I'm going to demonstrate how this one works, again with my own playing, and we're going to do a little bit of the Outlaws, Green Grass and High Tides, see how this thing reacts, and here we go. Okay, hopefully that wasn't too painful, and you probably noticed that I swapped out the white Christmas light for a green one just for a little change. And now let's talk about some more modifications to the circuit. One thing you might want to do is just eliminate all of this dangerous high voltage stuff over here altogether and replace the incandescent lamps with LEDs. If we do that, then we can replace these TRIACs with Darlington transistors and run the whole thing off of a 15 volt power supply. And that's the modification we're going to look at next. Here's the circuit, and you can see I've taken out the TRIACs, replaced them with tip 120 NPN Darlingtons with 1 k ohm series base resistors. Now, as far as the strings of LEDs go, this top row here is the low frequency, so I'd probably make these blue. And with a 15 volt supply rail, we could probably put 4 or 5 of them in series before we'd get too many barrier potential problems, but you can experiment with it and see what works. I used green LEDs here for the mid-range, and again, I could probably put 6 or 7 in series without any problem. And then finally down here for the high frequencies, I use red LEDs. Since they have the lowest barrier potential, I could put more in series if I wanted to. But you can experiment with it and see what works best. Now, as far as these middle op amps go, I reduced the feedback resistor pot to 50 k ohms from 500 k because I don't need as much gain to drive the Darlingtons. And I stuck with the same coupling capacitor values here for my frequency selective section of the circuit. Now, I didn't breadboard this one. I thought I would try a little fancier filter circuit here, and the modification I made there is shown in this last version, where you get a little bit better discrimination between the 3 frequency bands. I'm not going to go through the analysis of these circuits, but they do work a little bit better. And now I'll demonstrate how this one works using 3 LEDs in each channel, and I'm going to play a little bit more Stone Temple Pilots, and this time it's going to be some Sour Girl. Okay, well, that's the last time today you're going to be subjected to my guitar playing, and it pretty much wraps up today's video. Now, personally, I like the incandescent bulb versions of color organs better. They're just, I think, a little nicer and more classic looking, but you can get nice LED versions too, and if you needed to string together more LEDs to get, you know, greater illumination and so on, you could always increase this power supply voltage and use as many as you can squeeze in there. Now, the circuits can get really complicated. You can have active filters in here and all kinds of stuff like that, but hopefully this was sufficient to give you an idea of how these circuits work. And remember, sometime down the line we're going to talk about op amps and how to design circuits with them, and actually how to design the circuits that go inside the op amp. We're going to design differential amplifiers and current sources and level translators and stuff. So there's a whole lot of stuff to look forward to in future videos, but we're going to jump back into the vacuum tubes in the next video. So until then, I'll see you guys around.